Hi everybody. This is the first of two lectures scheduled for Chapter 3. The title of Chapter 3 is Theory of Errors in Observations. And basically what we're talking about is trying to predict how well data describes a particular physical event. So this is an area of interest to statisticians, and it's also an area of interest to people who take multiple measurements, such as surveyors, where there are different levels of accuracy and precision of measuring equipment, and where we may not get exactly the same answer every single time. So what we're really asking every single time when we take a measurement is, what number plus unit best describes this data set? So today, this lecture is scheduled for February 5th, and it will be the first of two lectures on Chapter 3. The second, which is scheduled for February 7th, will be more the nuts and bolts of how to do the math to make these calculations. Today's is more about the theory of how we come about these ideas and sort of explaining why we need to work with these ideas at all. Sometimes it's hard to understand that if what you're used to is measurements or numbers representing a piece of data without really giving it much thought. So we're going to talk about sort of some of the things that can affect that idea and those types of measurements. So to begin with, this is a picture that exemplifies the difference between accuracy and precision. And any of you who have shot a firearm before, done target practice, would recognize the bullseye. Or if you've thrown darts, this is another good example. If you look at figure A, you'll notice that we have a grouping of shots that are very close to each other, but they are very far away from the intended bullseye of the target. This sort of a situation represents shots or data that has a high degree of precision. Precision meaning that the pieces of data are close to each other. So we have a high degree of precision, but we have a low degree of accuracy, because accuracy would indicate that we would be right in the middle of the bullseye. The third bullseye, letter C, has a high degree of precision, meaning the shots are close together, and also has a high degree of accuracy because they are at the intended target, or they describe a winning set very well. And B is really a low accuracy, low precision type of a situation. Low precision because the shots are very far apart. Low accuracy because they are not in the bullseye. Now there's another strange type of a configuration that would be low precision but high accuracy, and that might be if we had a shot here on the left-hand side of the circle, a shot here on the right-hand side of the circle, a shot here at the top, and a shot here at the bottom. So the shots would be very far apart, but the average of those shots would be right in the middle. Now, it's not going to win you a trophy, but that's just an example of what low precision, high accuracy would look like. Accurate, and often the reason I'm kind of dwelling on this, in everyday conversation, we often use the terms accuracy and precision to mean the same thing. But scientifically, they are not the same thing. They're very, very different from each other. Precision, high precision with low accuracy almost always represents a calibration error. That means that the shooter, the person who is collecting the data in this slide, has done a pretty good job or understands how the shots should be taken, but the sight is off, for example. So when this person is sighting, they probably have a scope that's been knocked off balance, or something to indicate that there's a calibration problem. Now, in order to be accurate, the scope has to be accurate as well. Another example of high precision but low accuracy is if you weigh yourself on a bathroom scale, but the bathroom scale is set to be 5 pounds light. You could get repeated measurements that were very close to each other on the scale, and yet none of them are going to be right, and taking more measurements is not going to make it more accurate because the scale is calibrated improperly at -5 pounds. So we have situations where, and we can determine these based on sort of the way that the data looks and the way we collect it, of high precision with low accuracy, high precision and high accuracy, low precision, low accuracy, or as I described, low precision but high accuracy. This is a frequency distribution, which may not immediately come to mind when you think about measuring the length of the distance between two chaining pins, for example. But any naturally occurring data will fall into this type of a pattern. What it means is that the most number, if you're measuring, let's say that you're fishing and you catch 300 fish out of a lake, and the fish have an average length of 12 inches. For normally occurring data that has not been skewed in some fashion, not only will the average be 12 inches, but the most common number would be 12 inches long. So the most common, there would be more fish that were 12 inches long than fish that were 13 inches long or 11 inches long. And this curve also implies that there would be the same number of fish that were 11 inches long as 13 inches long, and so forth. So this curve, which is, like I said, normally we call it a bell curve, but we also refer to it as a normal frequency distribution. What this really tells us is, like I said, that we have the average and the most common number tend to be the same, and that the numbers, if the data is normally distributed, drop off equally in each direction, or drop off at the same rate in each direction. It also says that out here in the tails, out where you have very low frequency, that data tends to be kind of rare. So this would correspond to very tiny fish in my example, and this would tend to occur with very large fish. Now, another time that a normal frequency distribution occurs, you have to have a lot of data to make this work. You have to have hundreds and hundreds of data points, which is also part of the subject matter for statistics. But if you have enough data to determine if it's normally distributed, you can analyze it using a lot of different methods of statistics, which is just trying to determine how to describe that data set. So another type of data that's been really analyzed over time are IQ scores. And IQ data is standardized or normalized so that the average IQ on most tests is 100, and it drops off equally from, say, 90 to 110, or in some cases 85 to 115, but the curve is very symmetrical. It also means that almost everybody has an IQ between probably 80 and 120, and that when you get down into the tails, it becomes less and less likely that a person would have that sort of an IQ. So depending on the scale that they use, depending if it's a Wechsler test or whatever, when you get out here, you're going to get a very small, maybe 1 or 2 or 3% of the population that has an IQ that's either extraordinarily low or extraordinarily high. And most people will cluster around the middle. The boxes under this chart represent bins or ranges of data. So the first bin, we don't really go on a complete curve. We just say there's X number of points here, X number of points here, and the average of each of those bins is the top of this curve. And that's referred to as a histogram, which is just another way of summarizing this data. This slide is a little bit more mathy once again. This Greek letter sigma is referred to as a standard deviation. And this is sort of what we were talking about. Here in the middle, you have the maximum number of occurrences and you have the average occurrence. And you come down to a point called an inflection point, which basically what it means is that the concavity of this curve, or the curvature of this curve, switches. So it's concave up and then concave down, or concave down and concave up, depending on how you look at this inflection point. But at the inflection point, mathematically, you're 1 standard deviation below and 1 standard deviation above the curve. That also means, for other reasons that we'll talk about next time, that when you determine the size of an interval that constitutes a standard deviation, that approximately 67% of the data will occur between 1 standard deviation below and 1 standard deviation above this line, which is referred to as the mean. Then if you go out 2 standard deviations out to here, you catch about 95% of the data. And if you go to 3 standard deviations, you capture about 99% of the data. And that's where that unusual or rare occurrence comes above the 3rd standard deviation, above and below this 3rd standard deviation. So these are just 2 more examples of normally distributed data. This is very tight, has a strong central tendency. This is very spread, but the shape of the curve, the overall curvature, the inflection point, the distribution of percentages of data between points is exactly the same. The shape, in other words. So we can make inferences that do not depend on how tight the data is clustered around the mean if we have the proper formula, which we will learn next week. Or not next week, but next lecture. So this is part of the left-hand side of the curve. So in other words, from here down to about here, and it sort of drops off instead of giving this tail. But what we're looking at then is the standard deviation and the percent of the data. So basically what it says is when you get to 1 standard deviation, if you follow this arrow, you capture 68.27% of the data. So specifically between here and here, 1 standard deviation below and above the mean exists 68.27% of the data in a normally distributed data set. If you go out to 2 standard deviations, you capture 95% of the data, and 3 standard deviations, you capture 100% of the data almost. You see there's just a little margin here between the black line and the 100. The actual number is 99.7. So you capture 99.7% of the data between the 3rd standard deviation above and below the mean. And so that's what makes it rare to go above or below. So you're only getting 0.03% of the data above or below that. When we start talking about measurement, when we have errors that are built into our measurement, they compound themselves on area or volume measurements. Now, in plane surveying, we're not very concerned with volume, but with area we are. And basically what happens is that if you have an area, this just represents the average measurement A, the average measurement B. If A could really be between here and here, based on how good the data is, or how accurate or precise the data is, and B really can go from here to here, our area could be as small as this, or our area could be as large as this. So the error actually multiplies and becomes greater when you combine measurements. All right, so this is what we're going to be talking about when we start talking about the math on the next lecture. So I will be posting that prior to February 7th. And after you watch that, I will give you a homework assignment for Chapter 3. So thanks for listening, and we'll talk to you soon.